Thank you very much, Irene. Great talk. I'm going to start reading the Slack questions that are already posted. For folks who are in the session, if you're interested in asking your question live, please raise your hand in the Zoom session and I will promote you to panelists. John, I see you have raised your hand. Let me see how to how to promote you to panelists. Just a sec. Oh, you may be muted.
I'm already, actually, I'm promoted. Thanks, Irene. Interesting talk, and it raises a bunch of really thought-provoking questions. So one that comes to my mind is, how did you decide on those particular APIs? For example, an alternative would be to pick much higher level APIs, which would provide deeper abstractions. And if you look at the networking side, for example, the sockets API is kind of challenged. It works only for TCP and honestly has been pretty awkward even for TCP. But if you want to do RDMA or other messaging protocols like HOMA, it just gets in the way. Whereas if you chose a higher level API, like RPCs, then there's lots of room under that to accommodate a variety of networking technologies. And a higher level API also leaves you more opportunities for doing cross-layer performance optimizations, which are really important if we want to operate at microsecond scale latency. Might even have eliminated issues like zero copy. So I'm curious, can you talk a little bit about how you ended up with the APIs you did?
Yeah, so that's a really great question. I think one of our goals when we started designing the paper was designing the system was to not only support things within the data center. We have a lot of applications that run outside of the data center and they consume a lot of CPU cycles for, kernel level networking stacks. And so I think an RPC-based system wouldn't necessarily have generalized to those applications. I'm definitely, I love the message-based and RPC-based systems. I like how they enable, new network interface or like new network protocols. They're more efficient. I really like that they better fit a lot of the messaging patterns for, applications. I guess I actually also had a question. So the interface actually is message-based. But it's not RPC-based. It's not stream-based, if that's what you were asking. And so I wanted to be sure that I was answering your question correctly.
Well, it's sort of halfway between. It's still based on, for example, sockets where you have connections and you have to go through an accept protocol and stuff like that.
Ah, right, okay. Yeah, I think that was really a decision to try to support as many legacy applications as we could.
Thanks.
Thanks a lot, John and Irene. Next, we've got Tao-Ji, please.
Am I audible?
Yes.
Okay. I'm Tao from UT Austin here. And it seems one of the reasons nanosecond scale context switching can be achieved with Demikernel is that it relies on the user coroutine to save its own state before yielding. And in contrast to a preemptive scheduler, which needs to save the progress, including the registers. My questions, I have two questions actually. One is that, is it trivial for the user to make a decision which makes the yielding efficient? I mean, do I have to make a hard trade-off, difficult trade-offs between my application logic and the time I need to have the IO stack to run the IO stack processing? And the second question is, will this lead to isolation problems between user coroutines, even when they are not adversarial, when I have poor coordination between those coroutines?
So first of all, the coroutines are not visible to applications. Applications don't see or interact with them. The Demikernel IO stacks run multiplexed on the same thread as applications. And so that's why we need to have a way to context switch. I think at the nanosecond latencies that we're operating at, sort of interrupts wouldn't have been practical. And so, essentially cooperative scheduling is the only solution. We haven't really explored like very complex coroutine scheduling. I think there's actually a lot of work that could probably be done there. We sort of, if you look at the paper, have a very simplistic coroutine sort of priority queue where we always give priority to the application if the application has work. And then if the application doesn't have work, then at that point, we try to perform like IO processing with the idea that eventually the application will run out of work because these applications spend most of their time processing IO. And so when they do, that's when we should go and fetch some more. I hope that answers your question. And then you had a second question. I already blanked on it.
Okay, thank you. Yeah, that answered my my first question. And the second question is, will it be difficult to for a user to isolate to do isolation between their coroutines, or because they even a non-adversarial coroutine can harm the work from other coroutines, and it might be very difficult to do.
Yeah, we talk about this in the paper as well. So basically, the coroutines are entirely controlled by the Datapath OS. So there's no possibility of applications, making decisions about the coroutines. The Datapath OS decides when to yield, and the coroutines yield when they basically don't have work or aren't able to make progress. Because we chose to share application threads, this does mean that the application has to enter the Datapath OS in order for us to do work. And so, yes, the application could not call the Datapath OS for a long time, in which case the Datapath OS wouldn't get to run and we wouldn't be able to run, TCP ACKs and things like that. Most of the applications we looked at, that would never happen because we're talking about microsecond applications where they're constantly processing IO. But if that were to happen, there's some alternatives we talk about in the paper. We could potentially put the TCP ACKs onto a different thread. But yeah, I mean, in general, we offer coroutines as a scheduling abstraction, but we've not really dug deeply into coroutine scheduling policies.
Okay, thank you very much.
Perfect, awesome. Irene, you got a couple of more questions on Slack. I'm gonna just read one of them and then we leave the rest of them for the panel discussion at the end of the session, okay? So one of them says, does libsdpk do stuff like reshaping IOs to fully exploit the internal parallelism of SSDs? And if not, do you think such things could improve the IO performance, even with additionally induced overhead of reshaping?
So yes, I think there are definitely things. Our SBDK storage stack is extremely, extremely simple and stupid. We're currently actually working on another system that's designed for essentially demi-kernel storage. I don't think I have time to talk much about that. So feel free to ask me some questions about it later.
We have 1 more minute. There is maybe a live question. Is this Edward? Feel free to ask your question, but hopefully keep it to 1 minute. Just.
Yeah, I wasn't sure if you noticed, my hand got lowered by someone else, I think. Anyway, I was just wondering how your approach compared to, or if you had looked at the libfabrics library, which is trying to do a similar thing. It's a library that provides a common interface across a bunch of different kernel bypass networking hardware. And it's something I've been using a lot in my work with RDMA devices.
Yeah, the libfabric interface is really, I feel like, I would say maybe like HPC focused. We're really focusing on distributed systems. So like Redis, things that perform a lot of RPC processing and in-memory accesses. And then also like sort of potentially wide area data center applications where libfabric wouldn't work. And so that was basically the reason we chose to do something different.
Okay, can you use libfabric as the low-level interface instead of, say, native RDMA if you want to support multiple kinds of hardware in the RDMA demi-kernel?
Yeah, absolutely. I think in some ways, though, I would say that RDMA and Demikernel are not exactly compatible. RDMA is really focused on remote memory access, and Demikernel is really focused on message passing. And so I don't know that you would want to do that, I guess, is the answer.
Okay, just I was thinking about another attempt to sort of unify interfaces across these new network devices.
Thanks a lot, everybody. Thank you, Irene. This is a very popular talk. You got lots of questions on Slack. Please feel free to answer them.
Yeah. Thanks.
Thanks to everybody participated in this discussion. Very good. Let's move on to the next talk.
Just hear it again. Irene, are you visible and audible? There you are. I do not see any questions in Slack. Please go ahead and ask them and I will try to call on you. Meanwhile, we did prepare a few questions just in case. Also, if you'd like to raise your hand and I can spot that in the Zoom, I will call on you too if you want to ask questions. So, Irene, you're using 100 gigabits per second NIC and the maximum TCP throughput numbers in figure 9 seem to top that at around 17 gigabits per second. But you get closer to 40 gigabits in figure 8. Is there some discrepancy I'm missing there?
Let me take a look. I would guess that we're using larger packet sizes.
Okay.
I don't have the paper right in front of me, but I think so
17 gigabits is due to relatively small message sizes.
Yeah, so we did some of the experiments with 64-byte messages and some of them with 1024 to measure the performance of the system with both smaller and larger packet sizes.
Okay, we're still waiting for questions on Slack, and I
thought someone had raised their hand, but I'm not sure. I'm also trying to hear concurrently.
Yeah, let me see. I don't see that in, but I'm not a Zoom user, so. Oh, looks like, yeah. Go ahead. I will put.
I think Info has a question.
Yeah. Let me see whether I did the right thing there. Did I make you an attendee? Is that the right thing?
Yeah, can someone help out and promote?
I think I just
analyst.
did.
Okay, sure.
Or did I do the wrong thing?
I'm not sure if I can.
I may have done the wrong thing entirely.
Oh, no.
Let me promote a panelist. Okay. Okay, go ahead and ask your unmute and ask your question.
Sure. Yeah. Hi, I'm Ino. Yeah. Thanks for the great work, Irene. Yeah, I'm from NUS, and actually, I cannot turn on the video, so I will just speak up here.
No problem.
Yeah. Okay. So it's very interesting that co-hosts. Yeah, I can turn on the video now. Yeah. Yeah. Hello. So yeah, it's interesting that your work handled lots of challenges in the Datapath OS architecture design. And you also mentioned that at the end of the presentation, there are still many remaining challenges in this direction. So I just wonder, could you just introduce one or two main challenges you still have in your work? Yeah, thanks.
Yeah, so there's a little bit of a hint at this in the paper, but I definitely hope that this paper is a paper that causes people to think about more better solutions. So a couple of examples of things that we really haven't dug into too deeply. One is coroutine scheduling. So we use coroutines for very fine-grained CPU cycle allocation to both the IO stack and application workers. There's been a lot of work on scheduling application workers and assigning them to RPCs, but not a lot of work on sort of how to balance the division of CPU cycles between the application workers and the needs of the Datapath OS. So I think a lot of architectures either just put the network stack on another thread or another core. And so I think it would be really interesting to think about how these kinds of systems should be scheduled. As Jeff pointed out too, we have 100 gig NICs, which means that a single core is not going to be enough to handle all of the load. Which means that we need to think about multi-core architectures as well. So then there's some questions of, how should the multi-core architecture work? Should there be one core that's responsible for polling for IO completions? Should there be another core just dedicated to background tasks, like sending ACKs for TCP? And this also varies across the different libOSs, right? Because with RDMA, the NIC is in charge of sending responses and ACKs and ensuring reliable delivery. And so with RDMA, there aren't that many things that need to happen in the background. TCP, on the other hand, has constraints around how soon ACKs have to be sent and other things that have to happen on time, essentially. And so that is another interesting avenue of research on sort of how to make sure that TCP tasks are scheduled in a timely manner. Then there's a whole area of memory management that we've barely scratched the surface of. I think memory management for kernel bypass microsecond scale applications is really understudied. And I think there are a lot of interesting problems that might arise when you have an integrated memory allocator that's serving as your sort of user level memory manager. So one of the problems that we definitely have thought about, and we're doing a little bit of work on, is the fact that if you want your entire heap to be DMA capable, you have to pin the heap. You have to pin everything that the NIC might want to access, because essentially the NIC needs to be doing its own address translation, or the user level driver is doing address translation that's sort of separate from the kernel. And so pinning memory is really bad if you want to be able to share that memory with other applications. And so, for applications that are probably not using most of their memory for IO, you could imagine doing some sort of IO working set estimation, right? In order to take a look at what things, which pages are most popular. The other ones you could decide to not pin and then copy instead. And there's relative flexibility within our interface for the OS to transparently do that. And then I think the last thing that is sort of really stands out in my mind is thinking about how to co-design the libOSs with hardware, right? We have a lot of programmable hardware, and we're really not leveraging it super well in the data center right now. And so, for example, when I talked about the TCP stack having background work, one way to reduce the cost of TCP, which people have looked at forever, is to sort of chop it up into different ways and offload things to the NIC. I think definitely it's time to take a look at what we might be able to do there. Whether TCP is even the right protocol is a huge question. So I think there's also a lot of work in the co-design space between hardware and software Datapath OSs. Yes, that was a very long answer to your question. But...
no, I see.
So
thanks for the clear answers. Yeah, thank you. Yeah.
So thank you, Irene. I think you solved the problem of not having any more questions because we also don't have any more time. And I think you did answer several of the chair's prepared questions that we had prepared ahead of time. So we wouldn't be able to ask you any anyway. So okay. Hold on, we may have a little time at the end for a panel. So don't go away. I hope you can stick with us. And so our next paper is going to be Birds of a Feather Flock Together, Scaling RDMA RPCs with Flock. And the presenter is Sumit Kumar Monga, who is